Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is going to be my third and final video on figurate numbers. Um, I'm doing a new series on the Math Lovers book. This is a 3-volume series I wrote from 2019 to 2022, and I'm up to chapter 2 of volume 1. I'm going to continue this series until I'm all the way done with the end of volume 2, and just to give you guys a little brief overview on these books. Volume 1 is the more recreational one. This is kind of high school level, sort of fun math. And Volume 2 is more academic. It's also a little more advanced. I'd say it's more first year undergraduate level, includes calculus as well as theory of functions and probability and statistics. And the third volume's a problem and solutions manual. And all of these are available on Amazon.com, by the way, in case you want to buy copies of these. You can buy them either for paperback and $30 a piece or Kindle $9 a piece. And I think they're a good read. I think, I would recommend you get them if you're interested in learning this stuff, or you can learn for free in this series I'm doing. Anyway, let's begin with today's lesson. So today's going to be pretty brief, by the way. I'm just going to talk about two final figurate numbers, which are known as tetrahedral and pyramidal numbers. These are both based on three-dimensional figures, and as you'll see, the formulas are kind of complicated. But anyway, let's begin. So I'll start with tetrahedral numbers, and like the name implies, a tetrahedral number is just the number of points in this tetrahedral array. And you're supposed to imagine this is a three-dimensional object. It's a little hard to represent three dimensions on a piece of paper because paper is only two-dimensional. But I tried to indicate that by using different colors here. And I show every level of this tetrahedron. And by the way, a tetrahedron is kind of the three-dimensional analog of a triangle. You just take any 4 points in space that aren't all in the same plane, and then you connect each pair of points with an edge, and that gives you 6 edges, and it also gives you a 3D figure. If you connect the edges, that's called a tetrahedron. And a regular tetrahedron is a tetrahedron in which all the edges have the same length. Anyway, so and you can kind of like you do with a triangle when we're talking about triangular numbers. You can fill in a triangle with circles. In this case, you can fill in a tetrahedron with maybe it's easier to think of spheres because three spheres are three-dimensional. So this is supposed to be a tetrahedron with a side length of 4, and you can fill this up with spheres 4 on the first level, the bottom level. These are the red spheres. There's 10 of them, I think you can see, uh, because 10 is the fourth triangular number. And then the next level is green, that has 6. So, and then the third level is blue, that has 3, and the fourth level is violet, I believe, or purple, if you like, and that has 1. If you add all those up, you get 20. So you can see the T4, I'm using a fancy T here because I don't want to confuse it with a triangular number, so I gotta use a calligraphic T or a script T if you like. Script T sub 4, that's the fourth tetrahedral number, that's equal to 20 in this case. And there is a formula for general Tn, script T of n. You can derive it. It's actually you're summing up consecutive triangular numbers when you do this. I can think you can kind of see that from this diagram. Here, you're just summing up the first 4 triangular numbers, and that'll give you 20. But in general, if you do it for general n, you get this kind of complicated formula I wrote on the bottom. It's equal to 1/6 times n. What is it? I have to look at this. 1/6 times n plus 1 times n plus 2. Um, and if you want to generalize it, you can generalize this form for arbitrary dimensions. I don't do it in my book, but for 2 dimensions is 1/2 n times n plus 1. For 3 dimensions, 1/6 times n plus 1 times n plus 2. Turns out for 4 dimensions it would be 1/24. That's also 24 is 4 factorial. It's the product of all integers up to 4. 6 is the product of all integers up to 3, 1 times 2 times 3. And then in the numerator, you have n times n plus 1 times n plus 2. Similarly, for if you were doing 4-dimensional, you would get n times n plus 1 times n plus 2 times n plus 3 all over 4 factorial. In general, if you wanted to do it in k dimensions, you would have n times n plus 1 times n plus 2, so on, up to n plus k minus 1. That's in the numerator, that's k terms. And then you divide the whole thing by k factorial. You'll just have to take my word for that. But that is the kth dimensional generalization of the tetrahedral numbers, or triangular numbers, if you like. So anyway, you do get this formula for t script t sub n. And you can plug in a number if you want. For instance, script c sub 10 would be 1/6 times 10 times 11 times 12. And that turns out to be 220, I believe. So if you had a tetrahedron whose side lengths were 10, you would have a total of 220 spheres inside of it. So that's tetrahedral numbers. And then there's another kind of three-dimensional figure you can do. Sorry about this. I was copying my page, and this turned out a little messy, but I think you can read it at least. So then there's also what's called pyramidal numbers. These are sort of similar to tetrahedral numbers. The only difference is that you have a square base. With a tetrahedron, you can think of a tetrahedron as a triangular pyramid, if you like. You start with a triangular base, and then you have an apex on top, and you just form a pyramid out of that. That's called a triangle pyramid, which is also known as a tetrahedron. But if you start with a square base, you get the kind of pyramids that the Egyptians built in Giza. This is what we usually call a pyramid, a square pyramid. Also turns out to be half of an octahedron. If you form the mirror image on the bottom, you would get what's called an octahedron, which is another Euclidean solid. It turns out a tetrahedron is an example. A regular tetrahedron is one of the 5 Euclidean solids, and there's a total of 5 of them. I might as well just tell you what they are since I've already told you a couple. So the tetrahedron is the simplest. That has 4 faces, if you like. And then there's the hexahedron, or the cube. Cube has 6 faces. The octahedron has 8, which, like I said, is like a square pyramid, but reflected on the bottom as well. And then there's 2 more. The more complicated ones are the dodecahedron with 12 pentagonal faces, and the icosahedron with 20 equilateral triangular faces. So you'll see that later in my book. I just thought I'd mention it here. But anyway, I kind of digressed. Getting back to pyramidal numbers. So now we know what a pyramid is. I mean a square pyramid. So I think you get the idea of what a pyramid is. And you can do the same game with this. I mean, you can think of this pyramid as built up in 4 levels. In this case here, this is I'm going to call this script p sub 4. So script p sub n is the pyramidal number where the side length is n. And I think you can see how this pyramid is built. If you start from the top, there's 1 sphere on the very top. That's the apex of this pyramid. On the second level from the top, there's 4. This is a 2 by 2 square. And on the third level down, there's 9. These are all square cross sections. So each number is going to be a square. So the third level is going to have 9 spheres. The fourth level, the level on the bottom, is going to have 16. So you get 1 plus 4 plus 9 plus 16, the sum of the first 4 squares, if you like. And if you add those up, you'll see that that equals 30. So script p sub 4 is equal to 30. And again, there's a formula. I don't want to derive it here, but the formula for script p sub n in this case is 1/6 times n plus 1. I think it's actually 1/3. Yes, 1/3 times n plus 1 times 2n plus 1. I think it is 1/6. Let me just look at this. I think it is 1/6. So in this case, we could verify that when n equals 4. We would have 1/6 times 4 times 5 times 9, I guess. Yeah, that does turn out to be 30 if you calculate it. And you could do it for a bigger number, like 10 again. Script p sub 10 would be 1/6 times 10 times 11 times 21. I believe if you do the math for that one, you'll find that equals 385. So that's how you get a formula for pyramidal numbers. And this is a useful formula because this is the sum of the first n squares. And there is a way to derive these formulas. I'm not going to go into it in this slide. There's what's called Fallhaber's formula. I don't think I talk about this in my book, but there's a famous formula from I think it's from the 16th century. There was a German mathematician named Fallhaber. It might have been 17th century actually. I think it was around the time of Euler, so I think it was the 17th century. But he derived a very nifty formula for the sum of the kth powers, like the first n kth powers of a number. And it's a pretty cool formula. Maybe I should have put it in my book, but anyway, this is just a special case of that where k is 2, the dimension's 2. And the triangular numbers are another special case. That's just the sum of the first powers of all the numbers up to n, or the sum of the numbers from 1 to n. Might as well tell you another story while I'm on the subject here. You guys probably, I don't know how many guys have heard there's a famous story about Carl Friedrich Gauss. He's considered one of the greatest mathematicians of all time. He lived in the late 18th and early 19th century. And he was a math prodigy as a kid. He was a childhood math prodigy. And there's a famous story about him. When he was 7 years old, I guess he was kind of a smart aleck, so his teacher picked on him in school, and he said, "Okay, you think you're so smart in math? Let's see you add up all the numbers up to 100." And he thought it was going to take him the whole class to do. He's just a 7-year-old kid. I thought he'd just add them, I guess, on paper, pen and paper. I don't know what they used for a pen back then, probably feather with ink. But he did it in like a minute. I mean, it was amazing. He was 7 years old. He did it right in his head. He didn't even write anything down, I don't think. And he solved the problem in 1 minute. The answer was 5,050. And the teacher was amazed. First, he checked himself. He spent the whole rest of the class, I think it was like a half an hour, checking his work, and he found out by adding the hard way that it was indeed 5,050. But Gauss used a trick. Gauss actually was able to derive a formula for tetrahedral numbers. I mean, the way he did it was by pairing up the numbers. Like he paired up 1 and 100. 1 plus 100 is 101. 2 plus 99, that's also 101. 3 plus 98 is 101. You have 50 pairs if you keep doing this, because you have 50 plus 51. That's going to be the last one. So you have 50 times 101. That's 5,050. And so that's how he was able to derive the formula for the nth, triangular number. And I think you can do I don't know if you can do tricks not quite that simple, but you can do tricks to calculate pyramidal numbers and all the Fallhaber formulas. There is some pretty neat tricks for calculating. I just thought I'd mention that. But anyway, that concludes my video for tonight on figurative numbers. This concludes my section 2.1 on figurative numbers. So thank you for watching. Long live math, and I'll see you guys next time.